Hello everyone, so today we're going to go over section 4.4, equations and graphs of polynomial functions. We'll begin with a review of quadratic polynomials. So here we have f of x is equal to x squared minus 5x plus 6. Now this is factorable. So once we factored, we'll have x minus 2 and then x minus 3. What that tells us is that the x-intercepts for this function are 2 and 3. Also notice that the constant term is 6, so the y-intercept is going to be 6. Okay, so if we are to graph this parabola, we will have the x-intercepts 2 and 3 and the y-intercept of 6. Okay, so in the previous course, there was also the matter of completing the square. So what we can do is separate out the first two terms. Oops. Divide 5 by 2 and square. So that would be 5 over 2 squared will be 25 over 4. And then plus 6. And of course, since we added 25 over 4, we should subtract 25 over 4 outside the parentheses. In this case, the leading coefficient is, the coefficient outside the parentheses is just 1, so we can just subtract 25 over 4. So from there, we can rewrite this first three terms as a perfect square. So this would be x minus 5 over 2 all squared. And then subtracting the fractions will leave us with negative 1/4. So what that tells us is that the vertex of this parabola would be 5 over 2 and then negative 1/4, which is right here. Okay, so what we can also do is use the fact that the parabola is going to be symmetric above the vertex, and we'll get a point 4, 6 here as well. Okay, so this parabola can be plotted, and it will look something like this. Oh, that doesn't look right. Right, the point is in the wrong location. Sorry about that. It wouldn't be at 4, 6, it would be at 5, 6. Okay, let's fix that. There we go. Symmetry. Right, so this is better. Of course, additional point on this parabola can be found using a table of values, but that doesn't seem necessary in this case. We have a very good plot, a very good sketch of a parabola with these 5 points. Okay, so the corresponding polynomial equation, of course, is the same thing, but with 0 instead of f of x on the left-hand side. And the idea here is that this is, of course, an equation, and if we factor the right-hand side, we still get x minus 2 x minus 3. And so the solutions to this equation is that x is either equal to 2 or 3. So the idea is that the solutions to the polynomial equations corresponds to the x-intercepts of the corresponding function. Okay. So from there, we can look at cubic functions. The graphs are plotted beforehand just because they are very complicated to draw. So we don't want to make any mistakes beforehand. But here we are. So let's look at example 1. It says sketch the graph of f of x equals to 2x cubed minus 5x squared minus 4 plus 3. Sorry, minus 4x plus 3. Okay, let's begin by finding a factor using the integral zero theorem. So in this case, we're going to try -1 first. So f of -1, 2, and then -1 cubed minus 5 times -1 squared minus 4 times -1, and then plus 3. See what we have here. This will be -2, and then minus 5, and then plus 4, and plus 3, which of course is equal to 0. What that means is then that therefore x plus 1 is a factor of f of x. So next step then, what we can do is use synthetic division to divide f of x by x plus 1. So setup looks like this. So the coefficients were 2, -5, -4, and positive 3. And on the left-hand side, we have -1. So synthetic division, 2 carries downwards, and then -1 times 2 is -2. Add together is -7, and then -1 times -7 is positive 7. The sum of -4 and 7 is 3, and then -1 times 3 is -3, which means we do have a remainder of 0, which is good. That's what we're looking for. And the quotient is 2x squared minus 7x plus 3. So once again, this could be factored in any number of ways. So for example, let's use maybe this color. All right. So we can use 2 and 1. Those are the factors of 2. And then on the other side, maybe -1 and -3. And once again, using this method means we are looking for numbers such that when we cross multiply like this, we will get -1, and 2 times -3 is -6. Added together is -7, which matches the middle term. So what that tells us is that the two factors are 2x minus 1 and also x minus 3. So combining all three parts, what we have is the following. And that is f of x is equal to x plus 1, the first factor found by substitution. And then after division, we factored, and we got 2x minus 1 and x minus 3. So what that means is this f of x function has x-intercepts at -1 from the x plus 1, positive 1/2 from the 2x minus 1, and finally 3. And the other piece of information that is relevant here, of course, is the y-intercept, which is just a constant term of f of x, and that would be 3. So notice that on the purple graph, we have the 3 here, the y-intercept, and then the x-intercepts of -1, positive 1/2, and positive 3. Okay, so the question that we might have is how do we know how far down the graph goes, or how do we know how far above the axis does it go, and things of that nature. And probably the best way to find those out is just to use a table of values. Although as long as the key points, and that is the x and y-intercepts, are plotted correctly, it will be considered a correct sketch. So as long as those 4 points in the right places and the shape of the graph is a cubic polynomial, that should be sufficient. All right, so also the second example is g of x. G of x is equal to negative x cubed minus x squared plus 6x. So it is also cubic, but luckily this time around there's a common factor of x. Actually, we can factor out negative x. So if we factor out negative x, then we're left with x squared plus x minus 6. And of course, that's also factorable. So we'll have negative x and then x plus 3 and also x minus 2. So what that tells us is the x-intercepts of this graph will be 0 from the first factor, and then negative 3 from the x plus 3, and also 2 from the x minus 2. The y-intercept of this graph would just be 0, since the constant term is 0 in this polynomial. And so yeah, so here are the points. Oops, that's the wrong color. Negative 3, the 0, and then the positive 2. Now, the reason why the graph is upside down is, notice that the leading coefficient in g of x is negative, so it has to come from quadrant 2 and end in quadrant 4. Whereas f of x, the leading coefficient, was positive, so it comes from quadrant 3 and ends in quadrant 1. Okay. So that's that first part. Now, sometimes we'll in polynomials, the same factor can appear more than once. So let's look at what happens if that occurs through the study of what's called multiplicity. So it says here, if a polynomial has a factor x minus a repeated n times, then x minus a is a 0 of multiplicity n, however many times it repeats. So far, the f of x and g of x example we looked at, those zeros have multiplicity of 1 because the x minus a factor only appears once. Okay, so it's also known as the order, but we'll keep it as multiplicity. So for example, this parabola that is on the left-hand side, you can see that it's the standard shape. In fact, we can have a very good guess as what the equation was. It was actually y equals to x minus 2 all squared. Right, it's just x minus x moved to the right 2 spaces. So the x minus 2 factor appears twice, so it has a 0 of multiplicity of 2 at x equals 2. And notice the behavior here. Since it's even multiplicity, the graph touches the x-axis and then goes the other direction. So it decreases flowing from left to right, and then once it hits 2, it increases again. So it doesn't cross the axis, it just touches the x-axis. Now, the function on the right-hand side, this is y equals to x plus 1 cubed. So the 0 at negative 1 has a multiplicity of 3. And notice that the graph goes through the axis, but on the left-hand side here is concaving downwards. And once we're past the 0, it's concaving upwards. So this is known as a change in concavity. And the point where it occurs is called a point of inflection. So if we're looking at a 0 of multiplicity that is odd and not 1, then it would have a point of inflection. Okay, so those are two possibilities aside from what we saw in f of x and g of x, which is the graph going straight through at the 0. Okay, so here's a couple of examples of such graphs. Now, if we look at example 2's f of x, that is x minus 1 squared, x plus 3 squared. A couple of things to note. Number one, it is degree 4. And positive. Think about what happens if we multiply everything out, then we'll definitely have a term with x to the 4 power in it. And it's going to be positive, that term. So since it's degree 4 and positive, we know that this graph is going to go from quadrant 2 to quadrant 1. Is even, degree, and positive. So that's what we have in blue there as the graph. The two x-intercepts are easy to find. They are already factored out. So there are x-intercepts at 1 and -3. The question that we might have is, how do we find a y-intercept? We simply let x equal 0. So if we let x equal 0 here and here, then we have -1 squared, which is 1, and then 3 squared, which is 9. So y-intercept is just going to be 9. So again, the important points are the y-intercept, which is right here, and then the two x-intercepts. And the general shape of the graph is that it goes from quadrant 2 to quadrant 1. Now, the additional piece of information that we have is that both of these zeros have multiplicity of 2. So the graph will just touch the x-axis at those points and then go in the other direction. Okay, so this is going to be the way that this graph gets drawn. Yeah, so the other piece of information that it says is determine the intervals where the function is positive and where it's negative. So the function on the left, f of x, is going to be positive everywhere except for when x equals -3 or 1. Because the y values there are 0, and 0 is not a positive number. So if we are to list the positive intervals, that will be x is an element of the real numbers, except for -3 and +1. Okay, and it has no negative intervals. Notice that the graph is never below the x-axis. Okay, so let's look at g of x. So we have g of x is equal to negative, and then x plus 2 cubed, and then x minus 1 squared. So once again, we look at first the degree of this polynomial. 3 plus 2 is 5, so this is a degree 5 polynomial. And it is negative because of the negative sign in front of the entire g of x right here. So we expect it to come from quadrant 2 and end in quadrant 4. It's odd and it's negative. Okay, which is what the graph looks like. The x-intercepts were already found, and they were at -2 and +1. Right, the x plus 2 cubed produces the 0 at -2, and the x minus 1 squared produces this x-intercept at +1. Okay, this is not the best spot to write that. Okay, I'm just going to move it to the left slightly. Right, so so the next piece of information is the multiplicity. So notice here that the concavity changes. It goes from concaving upwards to concaving downwards. It's really the only way to draw the graph. You really cannot have it concaving the other way, as in it cannot really be concaving downwards and then upwards here. It doesn't really fit that way. So yeah, but it is a point of inflection, so that's the kind of best way to draw that. The other piece of information is we already can find what the y-intercept is it's down here, and once again we let x equal 0 to find it. So in this case the y-intercept is -8. And of course the x-intercept at x equals 1, that has multiplicity of 2, so it has to just touch the x-axis and go in the opposite direction. So the only extra point that is really used to plot this well is here at x equals -1. And we can find out what that is simply by substituting -1 into the g of x. Okay, next up is the positive and negative intervals. So positive intervals, there's only really one of those. And that is when x is less than -2. It doesn't include -2 itself, of course, because if x were equal to -2, then g of x is 0, and that would make it not positive. And then we also have the negative intervals. There are, I think, 2 of them. So the first one is between -2 and +1. And then also when x is greater than 1. Notice that we excluded when x equals 1 in the negative intervals. Okay, so one more part to talk about after this. It's another version of talking about multiplicity. So it says here, example 3, we're going to determine the equation of the least degree for each polynomial function. So here it says cubic function, so degree 3 with zeros -2, multiplicity 2, and 3, multiplicity 1, and then a y-intercept of 36. Now, this is a tricky question, but the setup usually goes like this. So we have y equals, and then we have this placeholder here, a. Okay, we're just going to leave the coefficient here for now. And then the next part is constructing the zeros -2, so x plus 2. It has multiplicity 2, so squared. And then the other 0 is at 3, positive 3, so x minus 3, and has a multiplicity of 1. So we could write the 1 here, or we can just not write the 1. It is understood that it's to the first power. So the reason why we have to write the letter a as a coefficient kind of placeholder for now is we are given a specific y-intercept. So that is to say, if we let x equal 0 in this function that we have created, y is going to be equal to 36. So that's kind of the next step. This is what would happen. If we let x equal 0, y is going to be equal to 36. So if we were to simplify this, 36 is equal to a, and then 2 squares 4, and then times -3. So if we solve for a is going to be equal to -3. Okay. And of course, that wouldn't be positive. That wouldn't be possible if we didn't start with a kind of a placeholder coefficient a, right? If we just wrote this part here, then the zeros would be correct, but the y-intercept would be wrong. Let's say, for example, if we just didn't have the a coefficient, then the y-intercept would just have been -12, and that's incorrect. All right, so once we put everything together, then the final answer will be y equals to -3, and then x plus 2 squared for the first 0, and then x minus 3 for the second 0. And of course, the -3 in the front of the expression ensures that the y-intercept is 36. Second example, kind of the same thing. A cubic function has zeros 2, 3, and -2. The y-intercept of its graph is -18. So same kind of thing. So y is equal to, it's going to alternate the colors here. And then the three zeros are x minus 2, x minus 3, and of course x plus 2. So once again, if we let x equal 0, this is what we'll get. Oops, sorry about that. All right, so a, if we were to solve for a, would simply be negative 3/2. Yeah, so the other piece is there's another form of this question that could be asked, and that is instead of giving the y-intercept, a specific point on the graph could be given. So for example, let's say the cubic function has 0, 2, 3, and negative 2, and goes through the point uh, x equals 2, y equals 9, or something like that. So you can substitute. So we can substitute both the x and y value and solve for a. It will be very similar to what we just did. All right. So finally, this last part here is kind of the same thing that we looked at, but instead of giving the description of the function, we are given the graphs themselves. So in this case, if we start on the left-hand side, we have zeros at -3, -1, and 2. And the multiplicity would be 1, 1, and 2. And also a y-intercept of 6. So if we were to put this all together, we'll get y equals to a for now, and then x plus 3, x plus 1, and also x minus 2 squared. All right, from there, we can let x equal 0 and y would be equal to 6, since it is the y-intercept. So this would be 3, sorry, this would be 1, and 0 minus 2, -2 squared is 4. So a would be equal to 1/2 in this case. So putting it all together, the equation of the graph must have been y equals to 1/2, and then x plus 3, x plus 1, and x minus 2 squared. Okay. Question on the right-hand side, very similar. Right, -2 and 3 are the x-intercepts and the y-intercept of +3. So let's do the same thing. Y is equal to a, and then x plus 2 squared, and then x minus 3. Substitute in the y-intercept, so this would be 3 is equal to a, and then 2 squared is 4, and then -3. So in the second case, a is equal to -1/4. And we can put it all together. Y is equal to -1/4, and then x plus 2 squared, x minus 3. Okay. So there's two different variations of the same kind of question, where we're given some zeros and a y-intercept, and we're asked to find the equations of the function. Okay. So once again, that is about the equations and graphs of polynomial functions, specifically about cubic polynomial functions. And that's it for today, so thank you for listening.